Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video, all math-based of course, and as always an honor and a privilege to be serving you here today as it is every day here in my virtual classroom. Step on inside. Yeah, I got the Red Zone channel on the background. What you gonna do about it, NFL? Huh? You gonna try and copyright strike me? Bring it. Let's do some math though, however, guys. I'm going to be doing a review of sorts over the module that I've been covering involving polynomials, where we've been, oh gosh, looking at things like even and odd functions. We've been transforming graphs such as quadratics, cubics, anything in between. Doesn't really matter what kind of graph it is. The same ordeals of translations, reflections, vertical stretches and compressions, horizontal stretches and compressions. And then we've been dealing with, well, polynomials in general, the way that we can graph them, get their end behavior, odd, even, degree, things like that. So just all over the place, guys, but I have a nice big slick review. It's in the PDF in the description section down below if you want to check it out. And listen, we covered all the material before. For the sake of time and everything else, I'm going to rummage through this as if you've seen it. So this is a little more, it's a little less teaching, a little more doing, I'd say, for these ones here, if that's okay. I'll state what I'm going to do, but it's not bringing everything all the way back to where we've been before. However, I still need to write some things to make sense of them. All right, let's start with the first ones here, guys. I got 3 problems that I'm going to graph here, A, B, and C for number 1. And this is all based on taking some sort of new function based off an old function that we are going to transform in the following way. Hang on a second, I just wrote that wrong. A times f of, it's hard to talk and write this at the same time, bx minus h plus k. All right, we know that a is a vertical stretch and compression factor as well as a reflector. You can reflect over the x-axis with this. B is a horizontal stretch or compression factor, or you can reflect over the y-axis. H is a horizontal translation. K is a vertical translation. Okay, here we go. We have the graph f of x equals x cubed. Now to make sure that we know, x cubed primarily from a center has 1, 1, 2, 8 properties to the right, and then 1, 1, 2, 8 downward. It is an odd function, something that we'll go over later, but this is the basic nature of a cubic function to look like this. We're going to take this. This is our f of x. We're going to take this f of x and do certain things with it. Don't draw this one here, because we're about to change this thing up a little bit. But 1, 1, 2, 8, what do we do from there? So, part A, g of x equals, I'm trying to undo this here. Here we go. G of x equals 1/2, that's A, times f of x minus 3, that's h, plus 2, that's k. So we know that we're going to take our center and we are going to translate 3 units to the right and 2 units upward. So I'm going to go 3 over, 2 up right here, and that's that new center point. Now, what I'm going to do from there is I'm going to take this 1/2 and I'm going to basically squeeze everything closer to the center. I'm going to divide every height by 2. Instead of 1, 1, 2, 8, it'll be 1, 1/2, and 2, 4, as 1/2 is half of 1, and 4 is half of 8. And 1, 1/2, 2, 4 in this direction as well. I believe that's where that would go. 3 would go down to 27. Half of 27 is 13.5. That's 12 right there. 13.5. 13.5 would be somewhere down there. I'm not going to get a full point, but it would be about there-ish. So just to get the basic idea of this graph here, I'm going to go ahead and connect the dots for you. So coming from way up here, and shrink it to shrink, here we go. There is our graph. Not bad. Okay, so there's the first one. That's part A. Let's go to part B. G of x equals f of 1/3 x minus 4. The 1/3 means your b is 3. Remember, it's 1 over b, so b is 3. Minus 4 means k is negative 4. And again, I am doing this as if you've seen it before, so I'm getting these things out so I know what I'm going to do with them. K is negative 4 means we'll take our center and translate down 1, 2, 3, 4 units right there. And instead of our 1, 1, 2, 8 principle, now we're going to triple our x values and maintain the y values. Not 1, 1, but 3, 1. And not 2, 8, but 2 times 3 is 6, but 6, 8. So like that. Okay? So B is a horizontal stretch factor. We're going to take everything and make it 3 times larger than we would. And 3, 1 on this side. And 6, 8, can't really fit it again, but let's see, it would go about here-ish just to kind of get the point in. So here we go. Here is that graph-ish. Oh my goodness, let's try that again. Oh, one more time. Third time's the charm. Wait. You betcha. All right. Not bad. That looks pretty, doesn't it? Not because of the drawing. I like it when it's wider. I like to see that result. And finally, part C, g of x equals -2 times f of x plus 1. That a value is -2. The x plus 1 means that's an h value of -1. Remember, subtracting the negative there. So h of -1 means we'll take our center and we'll translate it here. 1 unit left, and that's where we go. The a being -2, the negative means we're going to flip this thing over. We're going to go from here to here. So when I say the whole 1, 1, instead it's going to go 1, 1. So 1, 1, 2, 8. But now it's so fast, it's not just 1, 1 anymore, right? A stretch factor of 2, vertical stretch factor, means we're going to double our heights as well. So instead of 1, 1, it's 1, 2. Now instead of 2, 8, it would be 2, 16. Now listen, that is off the graph. That's beyond off the graph, way down here, just to give you kind of an example. I don't know where specifically, but just to give you an idea, it is very low. But I want to still give you the idea of, although we can only plot this many points, here's a 1, 2 this way, and 2, 16. Let's see, 11, 12, 13. Oh, that's, I don't know. That's going to be way up here-ish somewhere, literally on this graph somewhere. But anyway, just to give you the idea, it's still an upward curve, guys. We're still taking this thing and going down through it. Vertical stretch factor just means extremely, extremely tall. But it still has that curve down through it, and it still takes off kind of in that direction. So doing what I can do, but there are the graphs. All right, those are the first 3 problems. Let's move forward. Okay, given some function f of x, this is number 2, given some function f of x, describe the transformation to the graph of f of x to produce the new functions g of x below. So this time, guys, we don't know whether it's a cubic or what, a quadratic or what it is. We don't care. We just know that it's some function that will be transformed, and we want to describe what's going to happen. I literally said the descriptions of the other ones, translate where, what kind of stretch factor and stuff. That's what we're doing here. So once again, let's pull out what values we do have here. This negative symbol means that a is -1. This plus 7 means that h is -7, as we established in the previous problem. And this -1 here means that k is -1. So the h and k have to do with the translation, and the a has to do with a stretch factor and or reflection. Now, the only difference that I do here that we got to change over on this other part right here is that although I started with my center with this, I have to describe my center, my translation last, because it's not just about translation the center, guys. We translate every point. I just translate the center here first because I'm going to do everything in correspondence to my center. But here we got to mention stretches and translation, stretches and reflections first. So I'm going to start with A, which is a vertical stretch factor. When we reflect vertically, whatever the graph is, we are reflecting over the x-axis. Reflect f of x over x-axis. So that flip has to happen before any translation, right? We flip it and then we kind of move it. So the translation here means translate horizontally. We're going to go 7 units left. That's the -7. I should type this. And 1 unit down. That's the k. There we go. 7 units left and 1 unit down. All right, part B, g of x equals f of, and there's a -2 times that x plus 1 quantity, and then plus 4. The b value here, we've mentioned this a lot before, guys. It's a fraction naturally inside there, just like the plus is naturally minus inside there. There's an inverse going on. First of all, b is negative. Second of all, it's a fraction in and of itself. It's -1/2. 1 divided by -1/2 equals -2. That's what's happening there. Just like before, just to mention one more time and to show you, this b was a 3 because it's 1 over b. That's 1 over 3. And 1 divided by what gives us 1? Gives us 2. 1 divided by 1/2 gives us 2. It's a -1/2. Moving forward. X plus 1, once again, we got an h of -1. And then this k value here will be 4. So let's start with the b value here. It's about horizontal business. We're going to reflect this thing horizontally. So whatever this graph is, we're going to reflect it over the y-axis. Reflect f of x over the y-axis. And because b is a fraction, that means it's a horizontal compression. We are going to be horizontally compressing. Horizontally compress by a factor of 1/2. And, we do these things on the graphs, just now we're describing it. And then we also translate 1 unit left. Oh, gosh, we have 2 more things to do. Translate 1 unit left, 4 units down. Or 4 units up, excuse me. Translate 1 unit left. And my handwriting is always bad on these ones when I'm trying to rush it. And 4 units up. Okay. Hey, moving forward, right? Number 3, given the graph of the cubic functions below, comma, period, whatever, write the specific function using the form. So here, now, I don't know, I guess they're forcing it on you using the A here. So we need to obtain a vertical stretch factor within this. If we need to use a horizontal stretch factor to justify what we did and then kind of convert it after, I'm totally fine with that. So right here, A times X minus H quantity cubed plus K. Same kind of thing, guys. Just understand what the transformations are based on your knowledge of what cubic functions do and how they operate. So in this cubic function here, we have a center. If you consider that your HK, your center is at 0, 2. It's like H is 0 and K is 2. That really helps with this. H is 0 and K is 2. Now, this graph has a reflective natural behavior. It looks like it had a flip over. Whether you call vertical or horizontal is irrelevant. Well, it is relevant. We should choose the A value. So the A value is going to be negative. We know this because otherwise the graph would have gone this direction. But this A value is negative. And then the next question is, did the stretch factor thing change? Is this a 1, 1, 2, 8? Well, I do see a 1, 1 here. Not this 1, 1. Literally, it's at the point 1, 1. But I see that it went over 1 and down 1 from here, or over 1 and up 1 from here. This just looks like a negative 1, right? I'm just applying the stretch factor based off the basic nature of a cubic there. And the B value doesn't, we're not applying a B value, at least in this case here. So we have our HK and A. We honestly can ignore H completely if you think X minus 0 there. So the equation becomes G of X equals negative 1 times the quantity, well, not even the quantity, this is just X. Here, let's write raw form, and then we'll simplify it so you're not too confused. And wait, where did everything go? Negative 1 times X minus 0 quantity cubed plus 2. That plus K is plus 2. So in a simplified form here, negative symbol, X minus 0 is X, we're going to cube it, and then plus 2. So it looks like it's just a cubic function that's flipped over and translated up 2 units. I mean, that's clearly what these things say, but that is what that thing means. All right, in this one right here, we have our center right here at 3, 1. That gives us an H of 3 and a K of 1 right there. Excuse me. This part gets a little tricky here that I'm looking at because it's not 1, 1, but it's 1/2, 1, and I see that 1/2 and I'm thinking of B. Right, I'm thinking of B. Now, they told us to put this in terms of A. That doesn't mean we can't use the idea of B the same way as we would before, such as G of X equals A times 1 over B times X minus H quantity cubed plus K. So this thing can still be involved in this way, but we're going to have to morph it into an A the way that we see that. So let's assume that A is still 1 in this way, that, there still is an up 1 principle. There's no vertical stretch. You can make it a vertical stretch, but there's no vertical stretch to note that we see right now. But I do see a B as a horizontal compression. The 3.5 means it only went over 1/2. So instead of going over 1, we divided this by 2. We shrunk it. That gives us a B of 1/2 right there. So in this very raw form, and we're going to have to do some simplification here, guys, but in this very raw form, it's G of X equals, the A is 1. I really shouldn't write it, but 1 times. Now, this is 1 over 1/2. If you're fine with me writing that as a 2, guys, if you understand that 1 over 1/2 is 2, right? The B being 1/2 means that's 2. I'm going to go ahead and write that as 2, okay? Times the X minus H, so X minus 3. This is cubed, and then plus K is plus 1. There's the raw form. Now, they want an A value only without that B here, right? What has to be understood here, this isn't read for being wrong, this is for emphasis, is the 2 is being cubed. The 2 is being cubed, just like the X minus 3 is being cubed. So let's do this, guys. Let's take the 2, let's cube it, and 2 cubed becomes 8. You can take that 8, take it out of the cubic portion of this. You can take it out just by doing 2 cubed right there. right? 2 cubed and x minus 3 cubed, like that. And 2 cubed is 8, and 8 times 1 is 8. So this becomes g of x. I know this is something that will be a little more daunting for my students because although I've transformed them for them, I haven't asked them to do too many of these things. So it's kind of something to go back to and say, all right, it's possible to do. You can turn a b into an a by doing that, right? The b was 1/2, and that makes an a of 8. And you're like, what the heck does that mean? Well, what that also means is this graph must have just, you know, the 1, 1, 2, 8 thing? 1, 1, 2, 8. Well, when b shrinks to 1/2, that becomes 1/2, 1. And instead of 2, 8, it becomes 1, 8. 1, 8 also sounds like a vertical stretch factor of 8. Instead of 1, 1, it's 1, 8. So that's the same thing, right? A horizontal compression of 1/2 is the same thing as a vertical stretch of 8, assuming that you only write one of them, not the other. So there's that version of that thing right there, guys. That's what you can do. All right, numbers 4 and 5. Here we go. The graph of f of x equals x cubed is reflected across the x-axis. The graph is then translated 11 units up and 7 units left. Write the equation of the transform function. Okay, reflected across the x-axis sounds like a vertical reflection there. That is an a value. That's a negative a value. It doesn't talk about a vertical compression or stretch, so I'm just going to say a is negative 1. It's translated 11 units up is a k value of 11, and 7 units left is an h value of negative 7. So there's nothing else there. So let's see. G of x is going to be the translated thing, and they say of x cubed. They say write the equation of the transform function. You can use the f of x equation if you'd like because they told us what it is. So I'm going to use the negative. So negative f of, and then x minus h, x minus negative 7, that becomes x plus 7, and then plus 11. So you can do that. If you wanted to put the actual x cubed version, we could say g of x equals negative quantity x plus 7 cubed plus 11. Remember what we do with this, x plus 7 goes into the equation, it becomes x plus 7 cubed, yada yada, like that. That's just kind of the nature of it. So either answer is totally fine. It didn't sound like they care. This is probably what I was looking at to begin with there. All right, and number 5, the graph of f of x equals x cubed is stretched vertically by a factor of 6. All right, that sounds like a again. So a is 6 here. The graph is then translated 9 units to the right. That sounds like an h value of 9. And 3 units down, that sounds like a k value of negative 3. Write the equation of the transform function. So in its f of x form, in that raw general form right there, we'll say g of x equals, and that's 6 times f, 6 times f of, and then that's x minus 9, and then plus, or minus 3. And then the cubic form of that thing, if you do f of x minus 9, that'll be 6 times x minus 9 quantity cubed, minus 3. Either or. As long as b is not in there, you don't have to do some extra stuff to just pull it out to just an a value there. They didn't mention any horizontal, any things like that, so there it is. All right, either or is fine there. Moving forward, guys, here we go. 18 minutes in. All right, let's do some inverses here. Find the inverse of each function. F of x equals 5x plus 10. So if f of x is that, let's find what the inverse function, right? Inverse function of x is by swapping x and y. Here's y, and let's swap x with y. X equals 5y plus 10. This is where we've established our inverse. But let's go ahead and solve for y again. Let's subtract 10 from both sides. And then let's divide both sides by 5. And you get y equals x minus 10 all over 5. You could also write it as like 1/5 x minus 2. That is dividing x by 5 to get a fifth of x, and then divide negative 10 by 5 to get negative 2. In case you ever want to graph out a slope-intercept form, I believe that since we're not going straight into graphing of any form, you can leave it like that. But of course, now we got to write it with the inverse notation. Inverse of x is x minus 10 all over 5. So a couple inverse operations and you're taken care of. We got y by itself. We're good to go. All right, part B. Same-ish, we got a y value here, and let's swap that with x to create its inverse, and then we'll go ahead and solve for that y. So in applying the inverse here, we're going to have x equals 9/2 y minus 5. Let's take care of the 5 first because that minus 5 happened last. Let's add 5 to both sides. I'll get x plus 5 equals 9/2 y. Now, a lot of people might have trouble with this 9/2 concept. Let me kind of write this up here and just go with it. They're like, fractions are intimidating. What do I do? If 9/2 is multiplying by y, what do I do? Divide both sides by 9/2? Technically, you could say it that way. If you want to do multiple steps, guys, don't write it as 9/2 y. Write it as 9y divided by 2. Maybe that'll help you a little more and say, okay, y is multiplying with 9 and it's dividing with 2. If you need to, guys, just go 2 steps at a time. Or yeah, 1 step at a time. Just go 2 steps in total. Multiply both sides by 2 first, but understand that's a whole quantity there. So that's 2 times x plus 5. If you want to distribute, I guess go ahead. Would they want to distribute? That's my question I want to ask myself. Would they want to distribute that? Sure. Let's distribute that so you know. That's 2x plus 10. So that equals 9y. And then divide both sides by 9 there. And then we get y equals 2x plus 10 all over 9 there. I don't know if they truly want to distribute or not. You can leave it factored as 2 times x plus 5 all over 9. But the inverse notation there is going to be like this. 2x plus 10 all over 9. There you go. There you go. There it is. All right, those are inverses. I did the inverses. All right, use composition to determine whether each pair of functions are inverses. So now I'm going to do a composition. I'm going to do either f of g of x or g of f of x, and we'll see if we get the same thing out when we take care of business here. I can't tell which one's preferred. You have fractions to distribute either way here, so I'll just go ahead and try f of g of x and press my luck. Let's just hope that we get x out. Our goal is to simplify it and get x out, and then if we do, we know we have inverses. If we don't, then we know we don't. All right, so f of g of x means I'm going to take f of negative 2 sevenths x minus 10 sevenths. That means this is going to take x's place in f's equation. So let's go negative 5 minus 7 halves times, instead of x, I'm going to write g's expression, negative 2 sevenths x minus 10 sevenths. Not much room on this one right here. It's kind of a lot to work with. I have to distribute now. I have to distribute the negative 7 halves into negative 2 sevenths x and the negative 7 halves into negative 10 sevenths. So there's a negative 5 still right here, negative 5. And then I have negative 7 halves times negative 2 sevenths. Well, a negative times a negative is a positive, so there will be a plus. I got 7 over 7, which is 1, and 2 over 2, which is 1. So that'll be a plus 1x right there through that distribution. Not as scary as I thought. And then negative times negative is another positive here. And then 7 times 10, well, 7 over 7. 7 over 7 is 1, and 10 over 2 is 5, so plus 5. Hey, look at this. That cleans up to all that right there. And now we have a negative 5 plus 5, which go bye-bye. So we do just get an x out. If we just get an x out, the answer is yes. These are inverses of each other. When you do a composition of functions and your simplification is just x, yes, it is. Cool. I didn't know if I expected it to be. It kind of intimidated me with the fraction stuff. Just a little bit. All right. This time, so we have an s, I think that's an s of x and t of x here. As I'm looking at this now, I'd rather distribute a 2 into fractions than distribute a fraction into integers. That's just a personal me call thing, because if I can bust those fractions, then I'd like to. So let's go ahead and let's do t of s, no, I'm sorry, let's do s of t of x. Let's do s of t of x, because I want to distribute that 2, negative 2 into it. So that's going to be s of 1/2 x plus 7 halves. So 1/2 x plus 7 halves will take x's place here. So that'll be 7 minus 2 times, instead of x, we're going to write 1/2 x plus 7 halves. 1/2 x plus 7 halves. I got to distribute a negative 2 into 1/2 x and into 7 halves. Now, thankfully, it looks like it's just going to be negative 2 divided by 2 there and negative 2 divided by 2 there. So what do we get here? We're going to get, there's a 7. All right, negative times positive is a negative, so minus. So negative 2 over 2 is negative 1 times x is negative x, so minus x. And then negative 2 over 2 is negative 1 times 7 is negative 7, so minus 7 there. All right, 7 minus 7 cancel, and we're left with x, right? We're left with negative x. Not quite the same thing. Maybe there's something to be stated about it being negative, but in the end, these are not inverses of one another. It needs to be a positive x for them to be inverses. Again, then maybe there's something to be stated. I don't really know what. All right, number 8. Identify whether the function graphed has an odd or even degree and a positive or negative coefficient. We're not asking whether it's an odd or even function. In fact, I reserved the whole last page for odd and even functions, even though we can go way fast on them. I just want to get a lot of practice in it just to feel it out, just because I can. I had a lot of room to do more things on pages. It's just whether it has an odd degree, odd or even degree, whether the leading term would be odd or even based on the nature of its end behavior, and based on the nature of its end behavior if it's positive or negative coefficient. What they mean is when we write something in factored form, and we could have tried to come up with an equation if these crossed proper intercepts, and we'd say like here's where they cross. In factored form here, well, not in factored form, in expanded form, what's going on? So listen, this thing goes down, it starts down, it stays down. That is the nature of an even degree. Even degree will have end behavior going in the same direction on y. Definitely even degree. Because they go downward, it's a negative coefficient, right? Those are the kind that flip over. So negative coefficient, that's what it is. I couldn't tell you whether this was negative x to the 4th, negative 2x to the 6th, or whatever it was. I couldn't tell you which one it was for sure. There is no stating for certain in any sort of way. This is a random sketch by a teacher. So it's probably no guarantee. I can tell you that it's negative and that this is an even number. I can tell you it's not an x squared though. X squared couldn't do a bend back like this. It can only do that. But anyway, I couldn't tell you the rest of that. But I know it's even degree and negative coefficient. All right, this one right here has a different kind of nature where it starts in one direction, it starts down and it finishes up. When I say start, I mean it comes from the left side from the downward angle and finishes up right there. It has a nice bounce back, but nothing we're talking about there. Question is it odd or even degree? Opposite directions here definitely calls it an odd degree. And the nature, the end behavior of an odd degree function, when it's positive, will start down, finish up. A negative odd degree function, which we might run into later, will start up, finish down like that. That's not what this is. This is an odd degree. It's a positive coefficient. And we move forward. That's all they wanted. There you go. All right. Number 9, parts A and B. Graphs each function. State the end behavior, x-intercepts, and intervals for which the function is above or below the x-axis. All right, well, let's start with the x-intercepts because that's going to help us graph it. I'll state the end behavior in raw form, and then we'll actually write it out later. So we have an x-intercept here of 1, right, because we're taking the opposite of the 1 minus 1. In zero product property, 1 minus 1 gives us 0. That's, the zeros of this thing. That's what we're trying to find out. Now, this also has what's called a multiplicity of 2, and we'll make sure to note that when we graph that thing. Multiplicity of 2. And then this is an x plus 3. That means if x plus 3 equals 0, x equals negative 3. That's the other x-intercept. So our two x-intercepts are x equals 1 and x equals negative 3. So 1, negative 3 are where this thing crosses the x-axis. This is a negative coefficient right there. It's negative. And this is an x squared times x. This makes it a negative x cubed graph. That means its behavior will be starting up and finishing down in some sort of way. It'll have some sort of whoop like that going. All right. So this one here, it does also feature what's called a multiplicity of 2 at x equals 1. That means that when it hits this thing, it won't go through it. It'll bounce off of it. However, whether it's from the top or from the bottom. So from the top, though, we do start from up here and we go down through. That's the negative cubic behavior of this. It goes down and through it. I don't know specifically where it hits here, but I know it has to turn around and it's going to bounce off this thing. That's the only possible way that it only hits these two intercepts and follows this end behavior like that. So it is a negative cubic graph, and that's what it will do. That's what it'll hit. That's what the multiplicity of 2 does at that spot. Now, some other things that they want us to mention here. We did mention the x-intercepts. We have those of 1 and negative 3. Okay, those are the x-intercepts. What about the end behavior? The end behavior, I kind of said it, starts up, finishes down, but that's not proper. Proper end behavior would state something like, as x approaches positive infinity, as we go forever in the right, to the right direction, where do we find the y values? Y approaches negative infinity. As we go forever right, we'll find our points forever down, right and down. You can see, right and down. That's where you can see those points going. To the left, where do we find our y values? Going way up there. as x approaches negative infinity, y approaches positive infinity. As we go forever left, we go forever up. That's the official syntax for end behavior on that. So there's my EB, there's my end behavior. And lastly, they want to find intervals where your function is above the x-axis and below the x-axis. So here's the x-axis right here. Things on the x-axis, such as the intercepts, these zeros, they're on it. They are neither above nor below. So as far as intervals for which they're above or below, we got to state that, like, okay, these y values right here, these x values right here that have y values that are above the x-axis. Remember, it goes forever left, guys. It still goes up and left in this direction. So it goes forever left. They are forever up. That's every point that's to the left of -3. So we have positive x values when x is less than -3. All the x values less than -3, you're going to get positive y values for everything up here. Now that's inequality notation. Interval notation would have said we go from -infinity to -3 like that, not including -infinity or -3 there. I'm not getting too deep on that with my students right now. I'm just working on inequalities for now. But either or, whether you use interval notation or that. Negative, when is it below the x-axis? Positive is above, negative is below. It's below the x-axis right here between -3 and +1. And then it hits 0 at 1. It's neither positive nor negative there. Remember, it wasn't negative or positive at -3 either. So at 1, it's neither, and then past 1, it goes beyond it as well. So it's negative in two places. It's negative when x is between -3 and 1. And then you'll also find negative values when x is greater than, I'll put a comma, when x is greater than 1, like that. In interval notation, we can unionize this. We can say between -3 and 1, or there's the union sign, or from 1 to positive infinity, like that. Okay. All right, here we go. Part B. I have what appears to be another cubic. I have x times x times x. It's an x cubed and a positive x cubed at that. That means we know that the behavior of this graph is going to have something of this form. The x-intercepts here are x equals -2. Take the opposite right there. X equals +3 right there. And x equals +1. Again, take the opposites of those. So let's plot those points. No multiplicities that are beyond, just 1. So x equals -2 there. X equals 1 here. X equals 3 here. No real tricks to this, guys. We start from the bottom. We finish at the top. We go right through these points. So I go up and through -2. Whoops. I go up and through -2 here. Back down through 1 and up and through 3 and finish up there. We're going to write about end behavior next. And that's it. There's really nothing else to that little part. Now we can state the end behavior. Let me move my picture here. Okay. End behavior. End behavior says as we go forever right, where do we go? So as x approaches positive infinity, we end up finding our y values going up toward positive infinity in and of itself. As we go forever right, we go forever up. And then as x approaches negative infinity, as we go forever left, we find our y values going forever down. Y approaches negative infinity. Now, we didn't end up doing any quartic functions here, or even degree functions, but if we went right and left, y would go toward the same direction. As x approaches positive infinity, y is positive infinity. As x is negative infinity, y is positive infinity. It would be something like that, or both down. And we didn't get to do that for these ones here. All right, when is it positive, or when is it above the x-axis? When is it below the x-axis? So positive is above the x-axis. Let's see when it is above the x-axis. Seems to be positive between these two x-intercepts here of -2 and 1. So between -2 and 1, we are positive. Oh, there's more. Hold on a second. And then it seems when we're greater than 3. So look at the x values that are greater than 3 as well. We're also positive there. So comma, when x is greater than 3, we are also positive. So like that. You could also use interval notation and state that we are between -2 and 1, unionized with 3 to positive infinity, like that. Negative, when are we below the x-axis? Apparently just between 1 and 3. Between 1 and 3 is, oh no, I'm sorry, I totally lost this. To the left of -2, and then between 1 and 3. So we have a couple lists right there as well. So we are negative, we're below the x-axis. You could put below if you'd like to. When x is less than -2, we're below. So when x is less than -2. And then also when we're between 1 and 3 right there on x. So between 1 and 3. And remember, we don't include those values because those are x-intercepts right there. If you put this in interval notation, we'd go from -infinity to -2, non-inclusive, unionized with 1 and 3, non-inclusive right there. The parentheses mean non-inclusive, square brackets would mean inclusive. All right, that's it for those graphs. So we've done everything now except for odd and even functions, not to be confused with odd and even degree. Odd and even functions have to do with some form of symmetry. That's what the whole back page is about. So let's get to it. All right, even and odd functions. Determine algebraically whether each function is even, odd, or neither shall work. So for these ones here, we know that a function is even if when we take the opposite x, we get the same y out as we're looking at right here. And then a function is odd when if we take the opposite x, we get the opposite y value out. And it's neither if neither of these occur right here. So what we're going to do here, this y, I really wish they wrote f of x or something like that just to kind of get, gain light of what we're going to substitute in a bit. So if this is considered to be f of x right here, let's see what happens when we take f of -x. So we're going to cube -x here, and then we're going to add a -x here. Now, cubing a negative value results in a negative number. So that'll be -x cubed, and then plus a -x is minus x. So f of -x equals -x cubed minus x. Now, what it appears to be, when you compare f of x and f of -x, all the signs changed. This is an expanded polynomial, simplified, all the signs changed there. That is the equivalent to saying factoring out the negative and having just the exact opposite here. You don't need to write that, but just the understanding is this is exact opposite of this thing right here. It's an exact sign change. It's not an even function. It's an odd function right here. This is definitely odd because of the result of what you see, probably from the first one right there. Just that result of what you see compared to this is complete sign reversal. The y values are the exact opposite of what they would have been when you plugged in the other x. So there's an odd. All right, number 2. Once again, this is an f of x. So f of x equals x squared plus x minus 3. Let's see what happens when we do f of -x. So now we're going to square a -x. We're going to add a -x. And then, of course, there's the minus 3. Okay. -x quantity squared gives you x squared. Because you square a negative, you get a positive. And then we're going to add a -x. That's minus x. And then minus 3. So f of -x gets you that result right there. Now, when you compare this to the original function here, you kind of have to ask yourself one more time, do we have an exact match? The answer is no, because even though that's x squared and that's -3, that's a plus x, that's a minus x. So there's a difference there. They're not the same. And then you got to ask yourself, is it the exact opposite? Did we switch every term? Well, the answer there is also no. Sure, these terms switch, but that -3 was never going to switch. You might know, if you're my student, you might know that if we don't cross at the origin, if there's some sort of constant in play here, it's not going to be an odd function, at least with regard to polynomials. It's not going to be an odd function, but it's also not an even function. This is a neither case. This is a neither case right there. All right, number 3. Again, I wish they had f of x. Looks like they use function notation after that. But f of x equals x to the 4th plus 3x squared. We're going to do f of -x here, and we get -x to the 4th power plus 3 times -x quantity squared. And then -x to the 4th power is positive x to the 4th power because it's an even degree. Again, you raise it to an even degree, you cancel out your negatives there. And then plus 3 times -x squared is plus 3x squared right there. You're going to really start to learn the things about with polynomials. If you have all even degree terms, then it is an even function. If you have an all odd degree terms, it is an odd function. There's something to that. So there's an exact match with your f of x and your f of -x here, and that is the result of having the same y for opposite x's. That's what even functions do. Even functions have the same y for opposite x's. This is even. All right, going to number 4 here, we got g of x. This time they use the notation. And let's see what happens here when we do g of negative x. We do 4 plus negative x quantity squared over 1 plus negative x to the 4th power. Now, some of this might feel a little mundane for you guys or tedious or what have you, but what you're doing is getting the understanding of no matter what you plug in for x, the results of this thing is what's going to happen. So, you know, what you're recognizing, and if I simplified it, by the way, what you're recognizing once again is you're getting the same exact values out. So if I did plug in a positive 2 here and then a negative 2 here, you know what to expect. It's going to be the same value you got as when you plugged in 2. These are the same. That makes it an even function. That's what's going to be happening. It's a rational function. It's a little different. You wouldn't know what this looks like as a graph. I wouldn't know specifically what this looks like as a graph, but I know how to graph it. It just takes you have to give me a moment to do it. But the fact is I can reflect it over the x-axis, and I'd get the same graph out on that side as I'd get on this side here. All right, number 5, h of x here. We have x over 1 plus x squared. So right here, what's going to happen, we're going to take h of negative x, and we get opposite of x up here over 1 plus, and then now you have opposite of x squared. So that becomes negative x all over 1 plus x squared. This one gets a little tricky for people because what you have to recognize is the question of, no, these signs didn't change, right? This wasn't a negative 1 minus x squared, and I get it, but this also isn't a polynomial. This isn't separate terms right now. Like I can't really separate this into separate terms either. You have to ask yourself if this is the opposite of, first of all, is it the same as this? No, because x negative x. But is it the opposite? Not just did the signs change, is it the opposite? That's why I wrote this one right here and factored out the negative 1 and said it's the opposite of what this was. See, this negative x also exemplifies that it's this fraction but negative. I could write the negative right out here and write it as x over 1 plus x squared. If it helps putting parentheses around it, I could do that as well. Guess what? This is the opposite of what this is. They are opposites. Doesn't matter that these turns negative. I don't want these to turn negative. If they did, then that's a negative over negative. It's a positive. That would actually be an even function. If it was, only one sign things has to turn negative in this case here, and this one does. The numerator turns negative. All the signs up there would have had to turn negative. I would have had to factor out a negative, but it did. My simple case of this, guys, is this is an odd function. Exact opposite y value from this one. Try and plug in some numbers. You'll see. Plug in 2 and negative 2. You'll see what I mean with it. And finally, number 6 here. Let's go ahead and substitute something in. Let's try to find the right. Let's do a color I haven't chosen yet. F of negative x here. On top, I'm going to get negative x to the 5th minus 2 times negative x cubed minus negative x. Okay, and that's all divided by negative x quantity squared plus 1. Okay, kind of running out of room on my own there. So that will give me, so again, to the 5th power, to the 3rd power, and to the 1st power here, all these signs will change. So, they'll stay negative. So negative x to the 5th, it becomes negative x to the 5th. Minus 2 times negative x cubed. So that will become negative x cubed times negative 2 is plus 2x cubed. And then minus negative x is plus x. And then all divided by the negative x that gets squared becomes a positive x squared. And then plus 1. So what you're looking at one more time, guys, just like this rational function, you have to ask yourself what's kind of going on. All the signs on top changed. Positive x to the 5th, negative x to the 5th, negative x to 2x cubed, So all the signs on top changed. That's also emblematic or symptomatic or whatever the kind of word is there of factoring a negative out of that top. If you'd like to just indicate that it's the exact opposite of what you had on top before, divided by that bottom. And listen, that is, I'm kind of running out of room, so I'm just going to point the arrow here. That is a negative on the outside if you'd like to. See, it makes your fraction negative. A negative on top, negative on bottom, whatever it is, as long as there's one of them means that can pull out of there. And we are getting the exact opposite of what we had here. It's the opposite of that. That is what an odd function would do. Odd functions do that right there. And we have that one more time. And I know people kind of, have trouble with that. You have trouble representing where a negative can and should go. It's just a negative 1 that's multiplying there. And that's what you get. It's an odd function. All right, a few more here. I'll go pretty fast on these ones. Now that we know that even and odd are just about, odd is about same x flip the x, you flip the y. Even function is about flip the x, keep the y. Neither is neither. Let's see what we get here. And sometimes you have to look at it. Use the graph to determine the function is even, odd, or neither. By the way, you have to assume for these ones that these just repeat. This is an oscillation of this one. So right here, assuming there's that repeat of this thing, what do we have? Let's find a point and let's see if we can make sense of what its opposite would be. So I get some x and some y right here. When I take the negative version of that x, am I getting the negative version of that y? Or sorry, what kind of y am I getting? In this case, it looks like I'm getting the negative version of that y. Some x, some y, opposite x, opposite y. You can see where we're getting this idea of what an odd function would be here, where it's symmetric across the origin, where you can rotate this thing 180 degrees and you get the same graph out. This is what an odd function would do. Unfortunately, we can't get some exact numbers there, but I think it's pretty symptomatic of that. You can kind of tell. And once again, with this thing kind of here, guys, it's going to be doing this up and down repeat. Just make sure you know that. But the question is it even, odd, or neither? It looks like it has some symmetry from the y-axis there, and I think I can trust that. I pick this point here, opposite x gets me the same y value. I pick this value x here, opposite x gets me the same y value. I'm getting the same y value, the same, not opposite, the same y value from opposite x's. That's what an even function would do, and that's what this thing is. It's symmetric at the origin. Excuse me, it's symmetric across the y-axis. It meets at the origin there, but this is an even function there. That's what that one's doing. All right, this one, number 9, doesn't have any symmetry that I know of. It's definitely not. If this reflected across the y-axis, I'd see the other part of the graph right here. If this reflected across the origin, I'd see this part of the graph right here. I'm leaning toward neither. But let's take a look. Let's pick a point. Like 2, 1 looks like there's a point right here. So either I should get negative 2, 1 if it was an even function, or negative 2, negative 1 if it was an odd function. And it seems to be neither there. Just at negative 2, we get this point down here that's like negative 5 or something like that. Definitely a case of neither here. There's no symmetry, even if they have like same lengths. They're not the kind of symmetry that we are trying to refer to there. Okay, last 3, and then we are all done. 10, 11, and 12. Use the table to determine if the function is even, odd, or neither. So for these guys, all we're looking for is, do opposite x's give us same y? Do opposite x's give us opposite y? If they give us same y, it's even. If they give us opposite y, it's odd. If they don't give us any indicator of it throughout, it's neither. So take a look at this. We get 4, 128. When I do negative 4, what do we get? Negative 128. Odd functions do that. Let's make sure all the others stay consistent. When I do 5, I get 250. Negative 5 better have negative 250. Yep. Like an odd function. And then 6 gives me 432. Negative 6 gives me negative 432. All right, this is definitely an odd function. That's what odd functions do. The opposite x's give us opposite y's of whatever xy we got. All right, number 11, let's take a look at 1, negative 3. And negative 1, we should either get negative 3 or positive 3. Oh, we get a positive 5. Yeah. See about that. If it's not the same or opposite y, it's not the symmetry we're looking for. This is a neither case. This is a neither case right off the bat. You can tell that those are already different right there. There's no reason to test anything else after that. Now, by the way, this table, this doesn't confirm everything, but this gives me, if this is all they give me, I'm going to have to go off that pattern and assume that the rest are good. Here, once I break it, I can disprove by counterexample, and this is a counterexample right there. All right, lastly, number 12 here. Let's take a look. Let's find some things. 1, 3, negative 1, also 3. Okay, opposite x's, same y. Something an even function would do. Let's check it out. 2, 0, negative 2, 0. Well, I couldn't tell here whether it would be odd or even because there's no such thing as negative 0. But it's still a 0. That's good. We expected that. And then 3, negative 5, negative 3, negative 5. Good. Opposite x is same y. Opposite x, same y is something that an even function would do. That's what this is. We are looking at, folks, an even function with that symmetry across the y-axis. And that ought to do it for this one. So there's that nice large overview, guys. This is Mr. Robinson. Thank you so much for watching. And stay tuned for more content in my virtual classroom later. Take care.